Every day, large quantities of used cooking oil are discarded as waste. But what if I tell you that this waste could become part of our transition towards cleaner energy? Hi, my name is Muhammad Fakhri Sham bin Muhammad Fadli from the Chemical Engineering Department at University Technology Petronas. My project is titled Investigation of Solvent Polarity Effects on Impurity Removal Efficiency in Biodiesel Purification via an upscale solvent-aided crystallization system. Biodiesel offers a renewable alternative to petroleum diesel and can be produced from resources such as waste cooking oil. However, producing biodiesel is only part of the challenge. Crude biodiesel contains impurities that must be removed before the fuel can meet the required quality standards. One of the most widely used purification method is water washing. The problem is simple. To produce a cleaner fuel, we should not create another environmental problem. Conventional purification can require significant amounts of water and generate wastewater that then requires further treatment. This raises an important engineering question. Can we purify biodiesel without depending on conventional water washing? My proposed solution is solvent-aided crystallization, or SAC, a dry purification technique designed to promote the separation of impurities without relying on water washing. But the effectiveness of SAC depends strongly on one important factor: the solvent. Different solvents interact differently with biodiesel and its impurities because of their different polarity characteristics. Previous research left an opportunity to systematically compare how different solvent types and dosages influence the purification process. Therefore, instead of simply asking whether SAC works, my research asked which solvent and what dosage provides the best purification performance. Among the 4 solvents investigated, 1-butanol demonstrated the best performance, achieving the highest FAME purity of 94.16% at a solvent dosage of 1%. At lower dosage, there may be insufficient solvent interaction for effective separation, while excessive dosage can reduce purification performance through increased miscibility. This identified 1% as the optimum dosage within the conditions investigated and demonstrated that solvent polarity is a critical factor in SAC performance. So how can this project become a catalyst for global change? I see its potential through 3 interconnected impacts. First of all, water conservation. By advancing a dry purification pathway, SAC has the potential to reduce dependence on water-intensive biodiesel purification. Second, circular economy. Waste cooking oil, instead of being treated only as waste, can become a feedstock for renewable fuel production. And lastly, cleaner energy production. Improving the purification process can contribute towards making biodiesel production more resource efficient and environmentally responsible. It represents an engineering approach where we do not only ask, can we produce renewable energy? We also ask, can we produce it more sustainably? With further optimization, solvent recovery, energy analysis, and scale up, this concept could contribute towards more sustainable biodiesel processing. Turning waste into energy is important, but ensuring that the process itself is sustainable is equally important. Through solvent-aided crystallization, or SAC, this project takes a step towards a future where cleaner fuel can also mean cleaner processing. I am Muhammad Fakhri Sham bin Muhammad Fadli, and this is my contribution towards engineering a more sustainable energy future.